Hello everyone. In this video I wanted to go through some more math and finish off what we started in lecture, which was going through the angular part of the wave function in 3 dimensions. So where we wound up was that we had a differential equation that looks something like this. We got to this point and we wrote down these two different sides, one side only involving theta, one side only involving phi. And we said, okay, that means both sides have to equal a constant. And we looked at the right-hand side and we said, well, that one looks fairly simple. We can solve that, and we say that this function here is actually just e to the im phi. So that part's done. Now I want to look at the left-hand side of the equation because that's a little bit more complicated. So what I'm going to do is I'm going to plug that in for g, and then I'm going to rewrite it a little bit. Actually, if I just plug that in for g, then this 1 over g times the second derivative of g with respect to phi just pulls down two factors of im, but I squared is -1. That cancels the negative there, and I get m squared. So this right-hand side just becomes m squared. And then I'm going to rearrange this just a little bit and write sine theta over f. Actually, I'll write it this way first. Squared. And then I'm going to move things around a little bit. But the main thing I want to do is I want to do a substitution here. What I'm going to do is I'm going to do a substitution. I'm going to change the new variables. Instead of theta, I'm going to use u equals cosine theta. And the reason for doing that is that then I get, okay, what's du? Du is minus sine theta d theta. And then sine squared theta is 1 minus u squared, because u is cosine theta. So I have that. And also I can look at these derivatives and I can say, well, what's df d theta in terms of df du? Well, it's du d theta df du. Du d theta is just negative sine theta. So this becomes df d theta equals minus sine theta. I ran out of room. Let me write that more cleanly underneath. Df d theta equals minus sine theta df du. So now I can kind of transform these derivatives and write an equation in terms of u instead of theta. And I'll skip a little bit of algebra, but I'm going to turn this into a slightly different form. So let me, using that transformation, I'm going to write it in this form, where I have 1 over f partial u, 1 minus u squared partial f partial u plus L equals m squared over 1 minus u squared. I've skipped a step or two of algebra here where I've kind of gone through and changed some derivatives and divided through by a sine squared, but that's mostly what I've done there. And in fact, after a little bit of algebra, you can rewrite this. And I'm going to skip again, maybe 1 or 2 steps, but I'm going to rearrange terms, and I'm just going to write it like this. Minus 2u partial f partial u plus, now move all these other stuff to the left, to the right-hand side, minus m squared 1 minus u squared f equals 0. Okay. So where I now get an f because I've gotten rid of this 1 over f in front, and I've done a little bit of other algebra to rearrange things. So what's so special about writing it like this? This was actually a recognizable equation for mathematical physicists even back in the day. Um, the solutions to this equation were in fact known. It looks kind of weird, but this is the one where I said this does have solutions, but not for any value of this constant over here, or sorry, there's L and M. For it to have solutions, L has to take the following, has to be the product of an integer times the next integer. So if L is, and L can be 0 here. The script L, the curly L, is the normal way of writing that. So it can be 0, or it can be 1 times 2, or it can be 2 times 3, and so on. And then M has to be between plus or minus L. So L, excuse me, greater than or equal to 0. M ranges from, it's also an integer that ranges from minus L to L. The solutions, what are the solutions then? If these constraints are met, the solutions are what are called generalized Legendre functions. That's not too important to know the name, but the point is they look sort of like polynomials in U, except for occasionally a square root creeps in. And remember, U is actually our substitution for cosine theta. So what we're going to get is we get this function of theta that has a bunch of cosine theta and powers of cosine theta. Now, the thing is, what's usually done with this is that they are combined. So, people combine the theta part and the phi part into a single function called the spherical harmonic. And there's a whole bunch of them. They depend on L and M. And so these are functions of theta and phi. And so they're the way the notation capital P is usually used for these generalized Legendre functions. So they're written as PLM, which is a function of theta, or actually really often written as a function of cosine theta, since that's the substitution we made. And then we have e to the IM phi for our phi part, which we already did that solution. And generally, you go and look these up. And the one thing I want to caution you about is that there are a lot of communities that use these different areas of physics and math that use these functions because they're widely useful. Remember, we got these by doing this Schrodinger equation in 3 dimensions, but even the potential didn't even come into it. So we didn't plug it in a potential. And honestly, the fact that we were doing the Schrodinger equation, all we really were doing was a second derivative equation. The fact that it had to do with quantum mechanics didn't even really enter into it very much. So this is an equation that actually pops up a lot anytime you're doing anything with spherical symmetry in physics. So you'll run into these spherical harmonics a lot. So that's why I wanted to do a video and show you some plots. Now there are some different conventions. Fortunately, Wikipedia mostly uses the same convention that our book does, which is a quantum mechanics convention. They basically just have to do with, do you put a minus sign in some of them or not, and where do you put the normalization? Or how do you normalize the functions? Because for us, we're doing quantum mechanics. Ultimately, this is just a part of a larger function, so we don't really care about the normalization too much, but there's a convention in quantum mechanics to normalize these such that they integrate to a certain constant, usually like 1 over 4 pi, or when you integrate over the whole sphere, that becomes 1. But some different communities do different things a little bit differently. So I wanted to flip over here to Wikipedia. Often what you do is it even has a table. Wikipedia has a page of, you can look up spherical harmonics. There's a whole lot of stuff here. We don't need to go into most of it. There's some nice pictures. I'll look at some also maybe live in lecture to kind of do a more interactive demonstration, but you can kind of see the shapes of these things. I want to spend a brief moment talking about that, but let me get to the table. So if we look at a table, there's a similar shorter table in your book. What what do these things actually look like? Because that's good to know. Let me erase this. Those are our spherical harmonics. It uses Wikipedia is just putting M as a superscript instead of a subscript, but it's really the same thing that I've written here. That I've written. There we go. Written here. Whether you use a superscript there or a subscript there is just kind of notation there. But for example, what's the 0, 0? The simplest one. It's really just a constant. In the book, they absorb the 2 into the square root, so it writes it 1 over square root 4 pi, but it's the same thing. So that's just a function. It's the kind of the easiest, it's the simplest function as a function of angle. It's just a constant. That's sometimes also what's called a monopole. It means it has no angular dependence. It's just a constant. There's no dependence on angle. What are some of the others? Well, if L equals 1, then M can be -1, 0, or +1. And you can see on the table here, I've got a few options here. I'm going to focus on, let me do y10 first, actually. That's going to be root 3 over 4 pi cosine theta. And then I have 1 plus or minus 1. I'm going to write it that way. Because you'll notice the functions themselves are actually pretty much the same. We have minus plus, so if it's +1, there's a minus sign out front. There's M equals -1, there's a plus sign out front. A little confusing, but whatever. 3 over, I'm sorry, this should be 8 pi. I move the 2 into the square root. I was right on this one the first time. Sorry. They have different factors out front. And this is sine theta, and then since m is not 0 here, I have this e to the I m phi part. So e to the I plus or minus m phi, and you can't see what I'm writing, so I'm going to flip over to that. But I've written out same functions, just slightly rewritten in terms of the constants. But I wanted to just look at a couple of these to kind of show and think about what do these actually look like. So these are functions of angle. So you can think of them as for every point on a surface of a sphere at every different angle, you have some number, and it can be a complex number. You can see in some cases we've got this complex number, but we want to look at, what are these functions doing on the sphere? So the simplest case, of course, was this just a constant. But here we have, let's look at this y10. It's just a function of theta, and it's just cosine theta. So what that means is, remember, theta is 0 at the North Pole and 90 degrees at the equator and 180 degrees at the South Pole. So that means the northern hemisphere here is positive and the southern hemisphere is negative. So I'm gonna try to draw that, but like positive numbers are red, positive numbers are blue, negative numbers are red. This looks like, I made it look like a Pokemon ball or something. But it goes smoothly from one to the other. So, at theta equals 0, this is just 1 times this constant out front. At theta equals 180 degrees at the South Pole, this is -1. And in between it goes intermediate values. So this is what, this L equals 1 term is what you would call a dipole. It has, it's positive on one side and negative on the other. So it's like having two charges. In fact, this arises because it's like having a positive charge and a negative charge, and then you take the limit where the separation is 0. And in fact, the same function arises in that case. So plus z minus z. What are what's y1 plus and 1 or y1 minus 1? You might be thinking those are sort of the same thing, except along the x-axis and the y-axis, and that's almost right. It's almost right because actually, to get the same thing along the x-axis, you have to take a linear combination of both of these. The way these functions are written, though, actually y11 is something that kind of rotates around one way, and y1 minus 1 is something that goes around the other way. So that when you add them together, you get something that goes along. I think when you add them, you get the x direction, and subtract them, you get the y direction, but I can't remember which is which. But you can kind of see what they look like. What do they look like? Instead of cosine theta, it's sine theta. So that means these functions are 0 at the north and south pole, but they're largest at the equator. And then around the equator, that's this phi. Then they go through basically a complex circle. When this is 0, it's just 1, but then when it's goes through to 2 pi, it cycles around a complex plane. And so that just means, depending on m, it has a plus or a minus sign. So that means one goes sort of clockwise, the other goes sort of counterclockwise. But when you add them together, you can get real functions. And so in chemistry, if you have done chemistry, things with this shape are called s orbitals. This shape, you might remember, these are p orbitals. This one in particular would be pz. It's in the z direction. What chemists would call px and py are basically combinations of these y1 1 and y1 minus 1 functions. So there is a function that looks basically like this, rotated in the x direction. That's a linear combination. So chemists like dealing with those because they like real numbers. They don't like things going off in weird directions. But in physics, sometimes we have to deal, since we're doing quantum mechanics here, and the phase is actually going to be important, it's in some ways simpler to work with these spherical harmonic functions. If we go up to L equals 2, then we get into what are called the d orbitals. And if you remember, there's even f orbitals beyond that, and they gave letters to them. But this actually is relevant for the hydrogen atom, but it's good to know, even outside for the hydrogen atom, it's good to know these wave functions, or what's sometimes called the multipole expansion. So L indexes, so L equals 0 is often called the monopole. There's only one possible independent way of doing that. It's just a constant. L equals 1 is a dipole, and a dipole is kind of like a vector. It points in a direction. So there if we're in 3 dimensions, then we have sort of 3 independent directions that we could point. So that's why there's kind of 3 of these functions. L equals 2 is called a quadrupole. And that's kind of a more complicated thing. There's 5 of those functions. It's technically what's called a tensor, which is math that we won't get into. But it's just a higher order fluctuation over the surface of the sphere. People talk about L equals 3 octopole sometimes. Octopole. I never quite remember how to spell that, if it's a U or an O in the octo, but these are important. In a lot of ways, they are these functions on the sphere serve the same way that, remember that we could express a wave as when we talked about waves, we said a general wave you can express as like a sum of a bunch of sine waves of different frequencies. So we talked a little bit about that, and that's an idea you'll come back to more formally in some later courses. But this idea that you can express some function as a superposition of sine waves is very powerful. Similarly, if you're talking about, that's a function on, say, a line. So if you just have a function of x, you can write it out and then do like a series expansion and look at it as a sum of sine waves. But for functions on the sphere, when you try to do a similar expansion, what you actually get are these spherical harmonics. And so that's why they show up so much, and why they wind up being so useful, is that you can describe any function on the sphere as a sum of a bunch of these spherical harmonics. And so often it's useful to break down something that's happening with spherical symmetry in terms of these spherical harmonic functions. So I think that's enough of me trying to sell these spherical harmonics to you. I'll end there and we'll pick up next time. Thanks for watching.